Okay, so for today, dimensional analysis and similitude. Um, it's quite boring chapter, I know, because it's like more on mathematics. But don't worry, it's really useful for fluid mechanics. So what we're going to do today is we want to understand what is dimensional, what is the dimension, what is unit. Saya rasa semua pun dah tahu. Dimension could be three dimension. Biasa kita dengar three dimension, one dimension. But dimension today, dimension yang saya nak maksudkan hari ini is slightly different. Unit pula you all very familiar with. For example, like meter, second, Celsius, what else? Pascal and everything. So for this topic, we really go into details on what is dimension, what is unit, and then we want to explain the concept of how scientists come up with very intelligent approach. For example, like if they want to know the states of the flow, then they will use Reynolds number, right? So how finally they come up with the Reynolds number itself? Kalau kita perasan, if you look carefully, Reynolds number is actually dimensionless equation. Not really equation. It's just actually the combination of few parameters, rho vd over nu, and then kita dapat satu value which is a number that doesn't have unit. So how come they get Reynolds equal to rho vt over nu? Ataupun sometimes they use rho u l nu, length, either length or diameter. U also referring to velocity, v also referring to velocity, and then mu, the viscosity. So there are actually a few theories that scientists use to come up with that kind of intelligence equations, like Reynolds number. There are a few more, for example, like Stokes number, Froude number, and then what else? Aerodynamic coefficient, and then few more things. Yeah, bila kita sebut coefficient, then definitely we know the coefficient usually just a number. But to get that number, there actually a step or a process to come up with that number. Okay, so kita akan belajarnya daripada first objective lah, to explain the concept and application of dimensional analysis. Second is to apply Buckingham Pi theorem in dimensional analysis. So what is Buckingham Pi theorem? Buckingham Pi theorem ni adalah dah masuk sekejap ya. Okay. So Buckingham Pi theorem, exactly the same pi, but slightly so biasanya kalau kita guna pi, dia dalam bentuk italic sedikit kan karakter dia, tapi untuk Buckingham Pi theorem ni dia adalah rigid straight pi. Adalah historical dia, you boleh refer in the textbooks for the details how they come up with that name, Buckingham Pi theorem. And then the last objective that we want to achieve is to explain and apply the geometrical, kinematics and dynamic model. For example, like if you want to have similarity between let's say apa nama ni, kereta yang kita test dekat dalam wind tunnel for example, and then we downsize, kita kecilkan kereta tersebut, and then kita kata kereta ini we want to test in the wind tunnel so that it can get the real situation of the car that running in the snowy situation for example, atau berdekat dalam dekat apa nama ni, dekat area yang very dry, ataupun with specific velocity and so on. So must be a step that we have to follow so that it's really follow the real dimension. Okay, so we will look on it later after this. So for dimensions and unit, I believe everybody know unit kan, a way to assign number to that dimension kan. Kalau contohnya hari ni COVID-19 kan, kalau kita pergi ke mana-mana institution ataupun let's say pergi mall, pergi market, even pergi masjid sekarang ni pun dia akan ambil temperature. So bila dia ambil temperature, dia akan keluar dalam bentuk numbers and then dia ada unit dia Celsius. So Celsius itu adalah unitnya, and then numbers itu numbers yang keluar sebelum unit akan refer ataupun akan letakkan kita ni dalam kategori mana kan. So that's unit. Very straightforward definition. I don't want to elaborate more. Dimensions pula adalah, dimension yang kita nak bincang ini adalah the physical quantity without numerical values. For example, kalau kita kata temperature tadi, unitnya adalah Celsius. Dimensionnya apa? Dia tak boleh lah kita fikir kalau one dimension, two dimension. No, it is not that knowledge. It's not that knowledge. It's actually different one. Dimension for temperature adalah lain. Kalau contohnya lagi, kalau kita contohnya sekarang pukul 3 petang. So 3 petang time kan, so kita ada second, unitnya adalah second S. But for the dimension untuk time adalah T, this one, big one, T. So benda-benda ni semua adalah benda yang termasuk dekat dalam 7 primary dimensions. So ada 7 primary dimensions. Mass apa? Kilogram kan. So mass kilogram, ada length. Length ni dalam bentuk meter unitnya, ataupun SI unit adalah meter, could be centimeter, kilometer. And then time, T, temperature. Electrical, nanti kita tengok apa dimension temperature. Electrical current, amount of light and amount of matter. So mass, length, time, temperature, electric current, amount of light and amount of matter are primary dimensions yang available ataupun yang di sekeliling kita. Contohnya dalam keadaan, contohnya kalau kita tengok bentuk dimensions of force. Force ni apa? Force equal to P times A kan, pressure times area, ataupun dalam unitnya adalah, ataupun boleh dikategorikan sebagai mass. Mass time dengan length, and then over time power of 2. Ni sama dekat atas ni lah. So basically mass sama juga, F equal to MA pun boleh juga. Contohnya pun sama, F equal to MA pun boleh. Maksudnya ini adalah mass, kilogram, A adalah acceleration, pun sama. So basically bila kita tengok carefully, dia ada mass, dia ada length, dia ada time. So bila kita tukar kepada unit, bila kita tengok, kita tukar dia kepada dimension, M, mass adalah M, length adalah L, T, time adalah T. So when you put them together, you can have M power of 1 because dia ada satu je value dia. L also 1 kan, satu saja, dia ada satu unit je. I don't have to explain in detail about this, right? Time ada power of 2, so T minus 2 because dia duduk kat bawah. Okay. Alright. So primary dimensions yang kita nak bincang dalam topik ini, the primary dimensions here doesn't mean that fluid mechanics yang address is actually well accepted in the scientific world that these 7 parameters are the primary dimensions. Okay, Maksudnya you boleh tanya lagi yang lain, contohnya apa lagi smell masuk ke dalam primary dimension? Tak ada kan? Apa unit untuk smell? Tak tahu kan? Apa lagi yang lain? Mungkin ada lagi dimensions ataupun parameter lain yang kita terfikir tapi tak termasuk dalam primary dimension. Primary dimension means that the common parameter that surrounded us, yang sentiasa kita jumpa. Definitely dia ada mass, M simbolnya, SI unitnya adalah kilogram, ni kita tahu. And then kita ada length, M meter, unitnya adalah simbol untuk dimension adalah L. Time, dia bentuknya adalah simbolnya adalah T. And then unitnya adalah second, S. Temperature, dia adalah theta simbolnya kan. Kalau tak kita confuse dengan time, they get confused. T dalam topik ini, T referring to time, not temperature. Banyak juga unit ataupun equation yang sebelum ni kita refer T as temperature, but in this case kita refer, yalah, because sebelum ni when capital T we refer as temperature, and then small t we refer as what? Time kan. But in this chapter we don't accept this. Kita carefully address the capital T is actually time. Okay, lowercase t kita tak refer kepada mana-mana dimension. Okay, temperature theta, SI unitnya adalah Kelvin, electric current ampere, amount of light CD candela, kita tak belajar lah ni kan. Amount of matter and mole, amount of matter, mole ni kita belajar banyak. I mean especially during your, I think kalau you ambil kimia ataupun physics masa high school ataupun secondary school, definitely you have experience with amount of matter ataupun mole. Okay, out of 7 primary dimensions, we actually only focus on the first 3. Okay, mass, length and time. Alright, you may ask me why not focusing on temperature, electric current, amount of light, amount of matter. Yes, these 4 primary dimensions will not be focusing in this chapter because we are dealing with fluid mechanics. Kita buat fluid mechanics saja. So fluid mechanics dia ada element temperature, but it's not really influential and very significant. Same goes to electric current, light and matter. But these 3 primary dimension, mass, length and time, we will definitely deal with these 3 primary dimension in any equations or in any calculations. So that's why we deal with mass, length and time only. Okay. Alright. Dimensional homogeneity. Apa maksud dimensional homogeneity? Dimensional homogeneity means when we do the summation of few parameters ataupun few equations, the unit and dimension must be equal, kan? Contohnya dalam kes ni nak bagi tahu ni lah, every additive term in an equation must have the same dimension. For example, like apple plus orange. Can we calculate that way? No, cannot. It has to be like, say, apple and apple, maybe this apple bigger ataupun this apple smaller. But when you add with the orange, it's not in the same status ataupun in the same equation theory. So it cannot be done like that. Same goes to the telephone as well. Just for example, this one. So it has to be very specific equations, then we can do the summation ataupun kita can add together or minus them. For example, like this one, if you do have, let's say, a particle ataupun a rigid body, and a rigid body here, ni adalah energy yang ada dalam satu rigid body, and then bila rigid body ini move to somewhere, dan dia berada kat sini, the delta ataupun the summation of energy in the particle are exactly the same. How come this as the total energy in the particle exactly the same? Because remember the continuity equation of the energy. Betul, dalam tajuk continuity equation kita tak deal dengan energy conservation. Kita tak cover dalam topik in the chapter 2 in the chapter 3 chapter 2 we not cover the energy conservation, but definitely if you do have something that moving from the ground to the floor to the air, or from the air to the ground, or pendulum. Remember pendulum kan? Kalau pendulum maksudnya you ada ball yang move to the top and then going down, you will see that actually running in different, for example, size should be the same. One second. You will see that the movement of the steel ball in the pendulum, it will the velocity or the speed of the steel ball is actually different based on the location. Because of what? Kita belajar dulu kan dalam high school, adanya kinetic energy kan, adanya potential energy and so on. So same goes to this equation. What I want to say in this slide, this page, the law of dimensional homogeneity, every additive term, meaning the terms that we want to add together, must have the same dimensions. So for example, like total energy in this particle, is actually equal to the delta. Delta means because the energy always conserve and it's changing, right? That's why we put delta. Don't get confused why you put delta all the time, because it's actually changing the value, for example. So delta U is the internal energy, delta KE is kinetic energy, delta PE is potential energy. So bila dia move, particle ni move, dia maintain plus delta KE plus delta PE. And then if you look carefully, how come we can add the internal energy, kinetic energy and potential energy, and then dia sama ataupun equal to the total energy. Kenapa begitu? Kerana setiap terms ni actually has the same dimension. Cuba kita tengok change in the total energy of the system. Ini yang saya sebut tadi. Kita tengok yang pertama, internal energy delta U equal to M, which is mass kan, and then U2 minus U1. Mana dia punya bawah ni, ke bawah ni, ke bawah sikit yang ni. Alamak, nanti saya padam dulu bagi nampak clear. So this one, delta U, and then you see mass, energy divided by mass, so it becomes energy. And then delta U equal to because mass dia ada satu M, and then L sorry, kat mana datang L power of 2 and T power of minus 2? Because energy and divided by mass, dia ada time kat dalam dia. So T actually di bawah dia, and then length ada kat atas, and then M kat depan, and then it become M1 L power of 2 and T power of 2. And then second one is kinetic energy, and kinetic energy also the same. You can have full extension of the terms in the textbook, you may refer there, but if you look carefully, all the same. mass time length power of 2 over time power of 2, then the same unit also occur here, and then the potentiality also the same. Then you see m power of 1, all of them, m power of 1, l power of 2 over t power of 2. Alright. Okay. Any questions so far? Okay, no. Okay, proceed. Okay, dimension and unit. Definitely, when we have shapes, geometry, specifically geometry, then we can have the dimension of the geometry. For example, like the geometry or the parameter of area. Area is, for example, like length times width, and then we can have m power of 2, and then it's equal to L power of 2. Velocity, ms, m over s, and then we can have L1 over t, ataupun macam ni pun boleh, kan? Tapi bila you letak di naik atas, then you can see the what we call this one, the substantial dia adalah power of -1. It's power of -1. And then same goes to volume flow rate, mass flow rate, force, work. Look carefully, work, energy and heat is actually equal to kilogram m power of 2, and then over s power of 2. So it's become m power of 1, l power of 2 over t power of 2. Okay, I hope everybody already have this slide. This slide is available in Kalam. You please download it and refer it. And it's very good to have this slide while I'm doing the teaching, so that you can have direct visual. Then if you do have any question, you can ask me directly. Okay, and then we continue a bit more. Dimensional analysis and similarity. So when after we know that primary dimensions and dimension itself, and definitely all the dimension that represent the parameters, for example like velocity, area, volume flow rate. Okay, sebab biasanya kita guna dalam bentuk unit kan, dalam kes ni kita guna dimension. Why we have to know the dimension, or kenapa, apa tujuannya kita nak come up with dimension, and it should be enough with the terms of the equations and also the unit. Why we still need to know the dimension? Because this is the answer. In most of experiments, to save time and money, tests are performed on geometrically scale model, not on the full scale prototype. Ingat tak saya cakap tadi? Okay? Kalau contohnya kereta Proton C70 tu kan, X70 tu kan. So X70 tu size-nya besar kan. Contohnya length dia adalah about 3 meter. 3 meter ke? Kan? About 3 meter. Length dia about 3 meter. So very big car, about 3 meter length. So we want to test the car in different condition, maybe 1,000 situations. For example, what happened to the aerodynamic on the surface of the car when this car running at, for example, 250 km per hour. Kita nak buat sendiri ke? Boleh kan? Kita test dia. Kita drive pakai driver pelumba tu, dan kita bawa kereta dengan 250 km sejam, 250 km per hour. But if you want to have different situation, for example 250 km per hour, but the weather is wet, contohnya tengah hujan ataupun after raining day, and then it's very slippery, the road very slippery, dia mudah skid, ataupun dalam keadaan yang very dry. So banyak sangat situation yang boleh kita consider. So takkan kita nak buat untuk semua kan. The best way to do the test or the experiments is by having the real experiments. For example, like using the wind tunnel. So if you run X70, Proton X70 in the wind tunnel, usually we won't do the real size. Kita akan downsizekan dia. Contohnya 3 meter, tapi kita letaklah dalam kita punya wind tunnel. Contohnya wind tunnel, kita ada satu dekat UMP, kita tak ada wind tunnel yang besar, kita ada satu je kat Karif tu, kecil je. Saya ingat saya dulu kerja Pro 2 sebagai R&D engineer, ada wind tunnel besar juga kat dalam tu, and then ada control room yang boleh manipulate in I think 100 situations, kan? Maksudnya boleh control humidity, temperature dan sebagainya. So, tapi size-nya kita terpaksa downsize yang betul-betul. Let's say daripada 3 meter ni kita buat 0.5 meter je. Kita kecilkan dia, jadikan hanya 0.5 meter length. And then definitely bila kita kecilkan dia size dia, so mass dia pun berbeza dan sebagainya kan. Even the dimension, the height, weight and everything. So bila kita kecilkan size, kita we have to make sure that when we do the experiment in the wind tunnel, let's say in wind tunnel, the reading, for example, like drag coefficient in the aerodynamic flow profile, kan, must represent the real situation. Kalau tak, buat apa kita nak buat eksperimen dalam wind tunnel, kan? So kalau nak dapatkan nilai ataupun value ataupun profile yang sama dengan real, that means we require a very sensitive similarity index or similarity comparison. That's why in this case they put care must be taken to properly scale the results. Thus, powerful technique called dimension analysis is needed. So we have to scale and everything, make sure that we can get the same one. You got what I mean? For example, like if you consider both of them to make sure that they have similarity, at least we compare Renault number. Kan? Kalau Renault number dalam real situation 250 km per hour as velocity, then we can calculate Renault number based on rho u v over Renault number equal to rho u times length, for example, length over nu. Okay, this one we name it as prototype, Renault prototype, and then this one also has Renault. This one usually we name as model, Renault model, equal to rho u L model. This one rho L prototype over nu. So definitely L, M and LP are different, right? Then we have to manipulate others so that we can have exactly the same Renault number. Okay, we will look at it later after this. Okay, so the three primary purposes of dimensional analysis are: first, to generate non-dimensional parameters that help in the design of experiments and in the reporting of experimental results. Okay, so basically kita nak jimat cost, nak jimat masa, tapi kita very sensitive on the outcome, on the results. Why we spend money or why we do the experiments if the results is not useful, okay? So we have to make sure that they have a very careful process so that the results really replicate or represent the real situation. Second objective ataupun purposes of dimensional analysis is to obtain scaling law so that prototype performance can be predicted from the model performance. Yeah, exactly what I mentioned just now. And lastly, to predict trends in the relationship between parameters. ialah bila you buat modeling, bila you modelkan dia dalam wind tunnel ataupun dalam anything lah, macam-macam boleh buat ni kan. Bukan hanya dalam bentuk otomotif kereta macam ni je, dan banyak lagi benda lain. Bila kita ada capability on the experiment, then definitely we can manipulate many things. Then we can have a trend or a pattern on the prediction of the performance of something, like say fluid. Okay, alright. That's why we have to have this chapter in Fluid Mechanics 1. You will deal with more analysis on the dimensional and analysis in the Fluid Mechanics 2. Because Fluid Mechanics 2 will be covering external flow. Kita kan dalam internal flow so far, remember? Kita dalam internal flow kan? Flow, water flow in a pipe, oil in the pipe, ataupun let's say static, fluid in statics. So still it's still ada boundary ataupun ada frame yang kita referring while we calculating the flow profile. But in the external flow, for example like kalau contohnya aeroplane, bila the aeroplane dia travel on air, the flight on air, and then flow ataupun wind yang force to the surface of the aeroplane, dia akan ada flow profile dia. Tu semua adalah external flow. You akan cover ni dalam Fluid Mechanics 2. Okay. So enough with the objective and example, a very brief examples on the dimensional, why we need to have dimensional analysis. Okay, how they do the dimensional analysis? There are many different ways to come up with the dimensional analysis, but the most popular one and most common methodology to get the dimensional analysis is by having the Buckingham. Remember I told you just now, Buckingham Pi theorem. Kita nak masuk Buckingham Pi theorem lah ni. Kalau you tengok dekat ni, Greek letter pi ni, pi is actually the Buckingham. Boleh je guna Buckingham Pi theorem. Denote a non-dimensional parameter. Ni adalah steps yang kita nak buat. Okay. So please be with me so that we can do step by step. Okay. In general dimensional analysis problem, there is one pi that we call dependent pi, giving it the notation of pi1. Benda pula ni kan, apa benda pula pi ni? Okay, you kena anggap macam algebra. Boleh? Ingat tak dulu kita belajar algebra, A times B equal to C. So we ask ourselves, what is B? What is C? What is A? So anggap anggap Buckingham Pi ataupun Greek Pi ni seperti itu. Boleh? Later after this, when we do the analysis, we will see that pi1 represent of what, pi2 represent of what. Okay, so please put in mind like that. Okay, the parameter pi is divided into two. Pi ada dependent, ada independent. So pi yang dependent usually kita note dia sebagai pi1, ataupun kat sini ada tulis ni ataupun dia tulis kat sini giving a notation pi1, dia panggil dependent. Adapun yang lain daripada tu, let's say kita ada tiga pi, so pi1 dah ambil sebagai dependent, so pi2, pi3 dia adalah independent pi. Meaning of what? Meaning parameter untuk pi2, pi3 adalah independent. Okay. Alright. So functional relationship between pi s, pi s pula, pi's, dia ada banyak lah. So usually bila kita letak di dalam form of equation, pi1 equal to function of pi2, pi3 and pi blah blah pi k. So apa maksud ni? Maksudnya adalah pi1 ni dependent. It depends Maksudnya apa? The value of pi1 really depends on pi2, pi3 and pi_k. Let's say kalau kita nak tengok kalau you ada bouncing ball contohnya. And bila you release bouncing ball, let's say bola volleyball and then you letak you release volleyball tu bola volleyball tu you release somewhere at the same level of your, let's say, your chest. Then you release the ball. Whenever you release the ball, kita nak tengok berapa tinggi dia bounce balik lepas pada tu kan. So dependent dalam kes ni adalah berapa tinggi bola tu bounce back on air after we release it. Yang independent dalam kes tu apa benda? Independentnya adalah contohnya tinggi bola yang kita lepas tu. Ikut suka kita lah, kita nak lepas sama tinggi dengan chest kita ke, sama tinggi dengan kepala kita ke, atau rendah. Betul? Apa lagi yang independent? Berat bola contohnya. Bola yang kita guna tu high quality dan dia ada spesifik berat dia. Kalau bola yang lain pula berat dia kan. So it's independent. It not depends on what. Kalau you let's say saya yang lepaskan bola ataupun you lepaskan bola, berat bola still sama, betul? That's what we mean by independent. Independent. Dia tak depends on something. Okay. Same goes to others lah. It's a few, just to name few examples. Okay, that's the functional relationship between pi. Still tak nampak lagi ni, baru sikit ni. Okay, to ensure complete similarity, the model and prototype must be geometrically similar, and all independent group must match between model and prototype. Ingat tak saya kata, contohnya kereta tadi, bila kita kereta Proton, bagi Proton lah semua kenal kan, X70 yang baru tu kan. Bila X70 Proton ni kita nak buat testing kat dia dalam 100 situations, but we want to save cost and time, kita buat eksperimen. Betul? So the real Proton X70, alamak dah terus ke sini tu So the real Proton X70, they ada specific size kan, spesifik berat dan sebagainya. So kita namakan dia sebagai prototype. Boleh? Bukan bermakna prototype ni tak boleh guna lagi. Dia adalah real size, that prototype. Bila kita buat eksperimen, let's say dalam rintangan dan sebagainya, kita downsizekan dia kan, kita kecilkan dia length dia, kita kecilkan mass dia, kita ringankan dan sebagainya. So kita namakan dia sebagai model. Okay, so that prototype model, that's what we're referring in this sentence. Model and prototype. Okay, must be geometrically similar. Yes, definitely, otherwise it's not comparable kan. And all independent group must match between model and prototype. Okay. Alright, to achieve similarity, dalam kes ni to achieve similarity, simple je. Definitely lah, kalau you ada pi2, kenapa pi2? Dia tak guna pi1. Sebab pi1 only refer to the dependent one. They depends pada something. But in this case, kita just play with the Proton X70 that have specific berat, dia ada specific length dan sebagainya. So dia adalah independent, not depends. Kita tak calculate contohnya kita buat dalam keadaan yang lain-lain Dia mesti dalam kes ni dia adalah independent. So kita namakan dia sebagai pi2. Jangan pelik. Kenapa dia tak namakan dia sebagai pi1? Because pi1, remember pi1 is dependent. So we want to check the performance of Proton X70 independently. So we put pi2. So pi2 model and pi2 prototype. Prototype, model. Sama je, kalau nak guna pi3 pun boleh, pi4, it's up to you. Pi_k ni apa? Pi_k is k referring to the number of parameters ataupun referring to the dimension. Okay. For example, dalam kes ni pertama macam saya cakap tadi, dimensional analysis and similarity to evaluate the performance of, let's say, this car. This is model car, this is prototype car. So usually we put with the notation of P. So LP is the length of the prototype, LM is the length of the model car, model car, yes. So there are three things that we always put in mind when we do the comparison study. In this case, we can name it as comparison study as well, which means we compare model car and prototype car. But we have to be careful, three things: geometrical similarity, kinematic similarity, or dynamic similarity. Okay, if you look at geometry similarity, the length scale equivalence. Dalam kes ni, we downsize the geometry. So you have to make sure length scale equivalent. Let's say kalau kita kata LP to LM dalam 1/5, maksudnya apa? Kita kecilkan asalnya size limiter, kita kecilkan kepada 1 meter. So the ratio is 1/5. So yang lain juga kita make sure scale-nya adalah equivalence. Or kinematic similarity. Let's say kalau kita modelkan flow, velocity P, nu P, PA, rho P, dengan velocity model dengan rho model also. Apa maksud kinematics? Kinematic is something that running, right? Moving. Betul? Dalam kes ni contohnya, kalau kereta ini bila dia run, bila dia tengah running, dia bergerak ke depan, dalam wind tunnel tu ada chassis dyno kan. So dia ada kinematics, dia running kan. The kinematics value of the car running on the chassis dyno kan, ni running on the rear road. This one running on chassis dyno kan. So chassis dyno and exit road totally different. So we have to make sure that when they do the speeding, let's say they speed up both of them untuk check quality atau performance of the car, actually they are comparing kinematics. So kita kena tengok yang ni lah geometrical kinematics, dynamic similarity juga sama, force scale equivalent. Okay, between a prototype car of length LP and model car of length LM, in the case of aerodynamic drag on the automobile, there are only 2 pi's in this problem. Okay, so kalau kita tengok tadi saya kata kalau kita just compare in term of, let's say, the geometrical, so pi to model equal to pi to prototype. But if you want to have let's say the output of the analysis, we can have pi 1. Output means what? Output means the dependent. It depends on what parameters ataupun quantity that we insert or we include in the experiment kan. So pi 1 equal to function of pi 2. Whatever value in pi 2 definitely will change the pi 1 kan. So pi 1 is equal to where dia kata ni where pi 1 equal to FD over rho V power of 2 L2. So FD ni adalah drag force ataupun aerodynamic drag. Sorry again, keep changing. Over rho V power of 2 and L power of 2, and then when you put them together you will see rho VL over nu, which is what? Which is the Reynolds number. Okay, let's do this example. Okay, okay, kejap Okay, similarity between model and prototype car. So this is model. This is a model of a car in the wind tunnel test section, and then they have moving belt. This is kalau you ambil belajar, kalau you ambil automotive nanti akan pergi detail chassis dyno. Ini chassis dyno. Okay, so the aerodynamic drag of a new sports car is to be predicted at the speed of 50 miles per hour at an air temperature of 25 degrees C. Automotive engineer, tengok dia kata aerodynamic drag of a new sport car to be predicted at the speed of 50 miles per hour. This one is not SI unit, but do we have to change it? We look at it later. At an air temperature of 25 degrees C. Bila kita buat fluid mechanics ni, whenever they say degree C or temperature, definitely it will portray a specific viscosity and density of the air, kan? Kita akan check dalam table kat belakang dalam textbook. So automotive engineer built a 1/5 scale model. 1/5 ataupun you boleh note dia sebagai macam ni, 1/5. Maksudnya apa? 5 meter yang prototype dikecilkan kepada 1 je, kepada 1 meter untuk model macam tu. It is winter and the wind tunnel is located in an unheated building. Maksudnya apa? Maksudnya dia bila unheated building ni, temperature dia low, rendah, very low. The temperature of the wind tunnel air is only about 5 degrees C. Tengok. Determine how fast the engineers should run the wind tunnel in order to achieve similarity. Tengok. Ini tujuan kita buat test, nak achieve similarity. Bila dia similar, geometrically similar, kinematic similar, dynamic similar between the prototype and the model, then the flow profile or the drag force or whatever value or flow pattern in the model, which means in the wind tunnel test section, is useful. Otherwise it's not useful if it's not similar with the prototype. Okay, so dia kata determine how fast the engineer should run the wind tunnel, kan? Okay, let's do this. The solution, they said, we are to utilize the concept of similarity to determine the speed of the wind tunnel. Assumption, we have to give assumption first. They said first assumption, compressibility of the air is negligible. Meaning what? Could be compressed air in the wind tunnel, because wind tunnel we can manipulate the speed of the air. It could be very high, but in this case we neglect the compressibility. Meaning what? Meaning it is incompressible. Then all the theory of the fluid flow and the fluid mechanics one is valid. So the wind tunnel walls are far enough so that it will not interfere with the aerodynamic drag force. The model is geometrically similar to the prototype. The wind tunnel has a moving belt to simulate the ground under the car. Okay. So what they do definitely you have to come up with the properties dulu. Sebab tadi dia tak bagi tahu properties, dia hanya bagi tahu air temperature, dia bagi tahu unheated wind tunnel dan sebagainya. So for air at atmospheric pressure at T25 degrees C, ini dekat dalam prototype kan, meaning dalam real situation. Rho is 1.18. Ni kat mana nak dapat ni tuan-tuan? Ni you kena baca dekat dalam table. And new 1.849 power of -5. Similarly at temperature 5 degrees C, darjah Celsius ni, ini untuk apa? Model kan? Tadi dia cakap Rho is 1.269 kilogram per meter cube, and the viscosity is 1.75. And then we do the analysis. Nak analysis apa? You can do exactly the same. New 2. Kenapa 2? Because we not calculating the outcome. We just calculating the real one, which is the independent one. The independent parameter. So pi 2 of model must equal to pi 2 of prototype. Okay, so pi 2 for model, how can we compare between the model and prototype? Yeah, definitely using the Renault number. So we just put down the Renault number for the model and for the prototype. So Renault number always row, you put everything here because different value kan. Row model and then V for the model and then L for the model. L ni adalah length over new for the model equal to row prototype V prototype L prototype over new prototype. Okay, remember what question asked us? Question asked us what is the velocity of the air in the wind tunnel that the engineer should run. Ni kata determine how fast the engineer should run the wind tunnel in order to achieve similarity between V mana ni? V dekat dalam air kat sini. So we do the comparison. When we do the comparison, we have to move everything so that we can have VM here. Kan? So bila kita alih dia rho P over rho M. Betul? Ni alih ke bawah dia. Kan? Okay, barulah boleh dapat apa nama ni? Dimensionless. Kan? Ataupun kita boleh take out lah the unit. And then what else? New. No, VP tak ada. Kita letak kat tepi. Kita letak lagi okay, new M. Ni pergi atas lah. New model over new P. And then kita letak lagi LP over LM. And then definitely VP. Okay, then easy lah. Quite straightforward. You just put every value here. And then LP dengan LM. And LP adalah 5. LM adalah 1. Kan, that's why kita dapat value ni lah. New P row untuk prototype model and include everything, then you can get the value. Okay, so similar here. And then VP. So 50 miles per hour. Maybe you can ask. Maybe some of you will ask. 50 miles per hour. Should we change it to the SI unit? Yeah, you could change to SI unit as well. No problem. But if you look at the velocity of air in the wind tunnel, the engineer should run at the speed of air in the wind tunnel at 221 miles per hour. Is so fast. Kan? Thus, to ensure similarity, the wind tunnel should be run at 221 miles per hour. Okay. Alright. Any question? Okay. So, how about if we're not using the wind tunnel? If we change from the wind tunnel to the water tunnel, so exactly the same steps, but we might have different rho and nu, which is density and viscosity. Kan? So dalam, let's say dalam 1/5 juga scale dia, maintain juga 1/5 scale model, and then you can have different rho, different nu, and then we put everything. You see the velocity of water, the velocity of water in the water tunnel, the engineer should run at the speed of 16.1 miles per hour. Rendah je kan? Rendah 16.1 miles per hour. Definitely lah, this should be an advantage of water tunnel, but there are many more things that we have to consider when we run water tunnel. Especially water tunnel, the density is very high and everything. And then we have to control a few more parameters, for example, like the shear stress, the size, so that it will not interfere with the flow regime and so on. And then the output later. Remember, we want to achieve similarity, but we want to achieve the similarity between prototype and model, so that we can make use the output or the flow pattern that we can have later after that. Okay. All right. And lastly, not lastly, this one is quite long. I hope to see you again tomorrow to discuss this, but I will introduce a little bit more. This is method of repeating variables. Remember I introduced you pi, and pi1 is dependent variable, pi2, 3, and even k is independent. And then if you look at this diagram, it's actually exactly the same example that I gave to you just now. For example, like this steel ball with specific mass and specific initial level ataupun elevation, we release it on the ground to the datum, and then it will go up. And then we want to see the elevation of the ball after it bouncing back to the air, how far it can go. So we can do the analysis in a few more things. So if you look at this, I want you to look at this first. So tomorrow we can have speedy teaching and learning. There are 6 steps on how scientists come up with how scientists make use of Buckingham-Pi theorem then by using the repeating variables to get finally the functional relationship of equation or term. So step 1, we have to list all the parameters in the problem, and then we count it as the number of n. And then after that, we from all the parameters that we list down, we check the primary dimension of each parameters, and then we do the reduction J as the number of primary dimensions, and we calculate K, ada N, ada J, ada K dah kat sini. So J is reduction of dimension that referring to the primary dimension, and K is the expected number of pi's. Okay, and then we choose J repeating variables, and then we construct K pi's and manipulate as necessary. And then finally, after having all the analysis, then we can write the functional relationship. Okay, look at this step by step. I will repeat again if you're not clear. Step 1. So exactly the same thing that I mentioned to you. We release the ball, the steel ball, from specific initial elevation, and then the ball bouncing back to the air, and then we want to know, we want to make use of several parameters that relates in this situation. So we list down all the parameters and we count them. Okay, and then make sure that any listed independent parameter is indeed independent of others, cannot be expressed in terms of them. For example, like radius of the ball, area of the ball is not independent and independent or whatever, because it's not what we call this one, it cannot be expressed in terms of the primary dimension directly. Otherwise we will have redundant things. Faham ke? Maksudnya apa? Ingat ayat dia berkata sekali lagi. Make sure any listed independent parameter is indeed independent of the others. Faham tak? Contohnya, let's say ball ni, dia ada specific mass dia, berat dia. So they have specific mass. The kilogram of the ball. So definitely they have specific radius, right? Or diameter, and even the area. So area, radius of the ball, are they depends on something else? No, right? But the mass of the ball, even the size, even the the gravitational acceleration when it go down actually depends on the radius of the ball. So we will not include them. Okay, what parameters that should be included? So list of relevant parameters. Z, dalam kes ni Z ni adalah This one. Elevation of the ball after the ball bouncing back to the air is function of what? Function of time, T. Function of WO, apa dia WO? WO is initial vertical speed. Let's say if you just free fall or you throw the ball, definitely will have different outcome, right? And then ZO, initial elevation, and then G is the gravity. So overall you do have the function. Remember, function ni tak termasuk function ni, it's just represent the mathematical expression. So yang ada dalam ni adalah Z, T, W, O, Z, O and G. Okay, and then after that we list down the dimension from all the parameters. For Z definitely L1. Ingat L apa? L adalah length, meter, kan? Okay, T adalah time, T1. Tadi saya cakap awal-awal tadi lower case T tak guna kan? Okay, I was wrong during that time. Meaning we also can use the lowercase t to represent time. Okay, you got it, Okay, and then WO, the way the initial speed of the ball, then definitely dia ada m over s lah kalau kita tengok kan dalam unitnya. Dalam kes ni adalah second, ni adalah apa nama ni, initial vertical speed, and then ZO is the elevation, mass again, and then gravity. And then gravity definitely they have m over s power of 2. Okay, kita dah dapat dah dimension dia. Okay, dah dapat dimension dia. Okay, so saya habiskan dekat step 3, then step 4 and 5 and 6 we continue tomorrow. So in step 3, after having this dimension, okay, apa kita buat dekat step 3? Dekat step 3 adalah we want to guess reduction of J, because K equal to N power of J minus J. K ni adalah number of pi yang kita nak masuk. Pi 1, pi 2, let's say ada berapa pi, kita buat macam tu. N is apa? Number of parameter. Kalau tadi dalam kes ni number of parameter kita adalah 5 kan? J ni kita nak guess. Maksudnya J ni adalah guessing. Tapi not really guessing lah. Usually we refer to primary dimensions yang ada dalam all the parameters. Dalam kes ni apa primary dimensions yang ada? Hanya ada L dengan T. So L dengan T, L adalah length, T adalah time. So both of them are primary dimension. Then J we put as similar with the number of primary dimension, which is 2. That's why A equal to, dalam kes ni sama 5 minus 2. 5 ni apa? Number of parameter kan tadi. 2 is J. Okay, and then K equal to 3. Okay, so definitely in step 4 we should have pi 1, pi 2 and pi 3. Ni adalah K, number. Ada 3 K kan dalam kes ni, pi 1, pi 2, pi 3. And pi 1 is dependent, pi 2 and pi 3 are independent. Okay, I think that's all for now. Any question? Any question guys? Tak ada Alright. Dekat note saya guna T power of 1.